Hoy vamos a hacer este curso de construyendo aplicaciones con bases de datos de vectores. El curso está hecho por Andrew Wenchi.
Welcome to this short course,
veremos qué
Building
nos aporta.
Applications with Vector Databases, built in partnership with Pinecone. Vector databases have become a key part of the infrastructure stack for building applications with large language models, specifically RAG or Retrieval Augmented Generation. But it turns out that they're useful for even more applications than is widely appreciated. In this course, you learn how to use vector DBs to quickly build applications in text similarity search, RAG, image similarity search, anomaly detection, recommender systems, and hybrid search, which refers to using simultaneously sparse and dense vectors. I know that's a lot of stuff, but that's why I hope you find this course useful. We'll cover a huge space of applications that you'll be able to build using vector DBs. I'm thrilled that the instructor for this course is Tim Tully, a board member at Pinecone. For over a decade, Tim had led teams of thousands of engineers as Splunk's CTO and then Yahoo's Vice President of Engineering. Tim had also developed the Pinecone Vector Databases command line interface, and I look forward to him sharing with us what he's been seeing from working with many people building on top of Pinecone's vector DBs.
Thanks, Andrew. I'm excited to be here.
I know I gave a long list of applications just now, but let me unpack briefly some of the key topics. Vector DBs lets you input a collection of vectors, say embeddings of documents if you're implementing RAG, and then send queries to it, such as an embedding of a new text query to retrieve documents relevant to your query. That's what made vector DBs a key component of RAG, where you fetch additional context for an LLM to generate this response. But it turns out that this ability to fetch similar vectors makes it very useful for many other applications as well. For example, in image similarity search, you can compute embeddings of images and then use the vector DB to quickly find similar images. Or you can carry out anomaly detection by checking if a new item has anything similar to it, and if it doesn't, then maybe it's an anomaly. There are a lot of details on how to implement these effectively, and Tim will dive into the specific mental frameworks and tips for building these applications.
Yes, as Andrew said, there are a lot of potential applications for vector databases. You learn about 6 of them in this course. First, you'll start by building a basic semantic search for text documents. Then, you'll move into building a RAG app. In the next step, you'll build a recommender system. Next,
Pues parece que aquí aprenderemos primero a hacer una búsqueda semántica, seguramente entre
you'll
vectores.
build a recommender system. Next, you will implement a hybrid search app for product recommendation. Then, you will build a child-parent image similarity app. And finally, you will work on an anomaly detection app based on a dataset of server logs. Through these examples, you will learn how to use a vector database to store and help you manipulate lots of different datasets. We'll draw from examples from Wikipedia text, pictures of faces, Quora text, structured data in the form of network logs, and a fashion dataset with paired images and text. One of the cool techniques that you'll learn about as well is hybrid search, in which you can use a vector database to manipulate vectors with both a sparse and a dense component. For example, in the product recommendations setting, you'll see how to use a dense embedding of images of clothing alongside a sparse embedding of a text description, and how to dial a knob controlling the relative weighting between the sparse and dense parts of the vector. By learning the foundations of vector databases and working on the applications you'll learn in this course, I'm sure you'll find even more possibilities to explore.
Many people have worked to create this course. I'd like to thank, on the Pinecone side, James Brake, Ram Srihashar, and Bear Douglas. From deeplearning.ai, Diala Ezzeddine and Eshmael Gagari have also contributed to this course.
In the first lesson, you will explore the essentials of semantic search, which will be used throughout the other lessons in this course.
That sounds great, and a lot of materials in this one short course. So let's go add a new dimension to what we can do using vector DBs. Let's go on to the next video and get started.
Vale, pues aquí seguramente aprenderemos, por lo que nos han dicho, búsqueda semántica entre vectores, un sistema de recomendaciones, similitudes entre padres e hijos, un sistema de similitudes y detección de anomalías.
Semantic search is a type of search that focuses on the meaning of the content being searched. As opposed to lexical search, which looks for literal or pattern matches to strings. This is an extremely powerful construct that has underlined most of what we see from text-oriented generative AI applications. In this lesson, you will be introduced to the essentials of vector databases and semantic search, which will be used throughout the next lessons in this course. Let's dive in. So we're going to build a very simple semantic search application using Pinecone. What we're going to do is start here on the left-hand side with the user and download a core data set and turn it into a series of vector embeddings and store it in Pinecone. Then we're going to build a simple question answer response system, and we'll ask what country has the highest population. And this will be a generic enough application that you can ask multiple questions against it as well. And so you'll see how that works in the example that we show in just a moment. So let's start off building the application. So what we'll first do is pull in import warnings so that we don't get warnings when we run the application, and then pull in the rest of what we need and what we'll rely on here. So we're going to use sentence transformer.
En principio nos bajaremos un dataset y guardaremos todo este dataset en la base de datos de Pincore, que es una base de datos de vectores que yo nunca he usado, así que veremos a ver qué tal.
There's a small helper utility that we created called Deep Learning AI Utils that handles some Pinecone and OpenAI key management for us. Okay, that works great. And then we'll use TQDM to see the progress of a lot of this work that we're doing. So let's download the core data set, right? And you'll see that we're taking here a subset of the data between rows 240,000 and 290,000 because it's so large. And we want to make it manageable. And what we can do now is take a look at the data set and see what we have. So you can see here, we looked at 5 rows of the data, and we can see there's questions, there's identifiers for the questions. All looks really great and usable. So let's start to prepare the data to ask questions. So what we'll do is get all of our questions. So we'll iterate over all of the questions and add it to a centralized array that has all of them in it, and we'll use extend here.
Aquí vamos, por ejemplo, que las preguntas tienen un identificador con un texto. Sí, básicamente son preguntas.
It has multiple elements in it. And then we'll build a list out of it. And then join it with the new line character so that we can look at it and see what we have. This is just a small delimiter here. This can be really as long as you like, but this makes it easier to see. This is going to put a hyphen across 50 times. This is going to put a hyphen across, and then let's look at the data. Oh, have a small missing a colon there. All right, so those are all the questions that we have, and then we'll prepare. You'll see that we have 100,000 questions prepared. So now let's get ready to turn this into embeddings before we send it into Pinecone. So depending on the device you have at home, you may or may not have CUDA available for you. And if you do, some of this will go a lot
tarjeta gráfica disponible.
Faster for you. If not, it's not a big deal because the data set's not that large. You'll remember we took a subset of it. Oops. And now we will use.
Y como vemos, hemos usado este modelo, All Mini lm y sentence transformer y transforma básicamente las preguntas en un vector de 388 dimensiones, este modelo.
Sentence transformer to transform this data into embeddings. All right, no CUDA, that's okay. We'll move forward. The data is not that large, but we have our model ready to go. And so now what we'll do is actually create a sample question and turn that into an embedding. And then we'll look at the embedding and we'll see, hopefully, that it's 384 elements wide. So now that we have an embedding, we have our data, we have our questions, we're going to start to use Pinecone a bit. And so we have a small utility that we prepared for you called DLAI utils, and we'll instantiate it here. And then we'll get our API key for Pinecone to use, and that's all you'll really need to use Pinecone. Okay. So now we're going to connect the Pinecone. And what you'll see here is the syntax is slightly different now. There's what we call a singleton object in Pinecone, and it just takes the API key. This is because it's connecting to what's called Pinecone version 3, which is a so-called serverless version of Pinecone. So what we'll do now here is...
Pues aquí pues cogemos la API key y lo conectamos con... Nos conectamos con la base de
that
datos.
utils package that we talked about earlier, the deep learning AI utils, and create an index name out of that. And we'll get our index name, and then we will start to connect to Pinecone. But before we do that, we're going to do a little bit of house cleaning and delete old indexes in case you're doing lessons out of order. And so what this will do is look for the index name that we just declared and see if it already exists in the Pinecone index, and we'll actually just delete it. Then we will create our index. And
si aquí en caso de que exista el índice, lo eliminamos y después lo recreamos aquí.
Let's just keep it clean here. This is saying we're going to use, I happen to know the answer to this dimension parameter is 384, and we saw that earlier. We're going to use cosine distance as the metrics to find similarity. And then there's a new object in Pinecone called the serverless spec. And the serverless spec simply just specifies what public cloud that your index runs on. In this case, it's AWS and US West 2. And now we will finally get a pointer to our Pinecone index. So say index equals pinecone.index, and we'll use the index name that we created just a moment ago. And if we say index, okay, great. If I say print index, we should get back a Pinecone index object. And it's going to take a little bit to run. All right, there's our index object. Finally, after we've created our Pinecone index, we can upload some data. So we will upload data using a batch size of 200 and a maximum of 10K vectors.
Vale, pues una vez hemos creado el índice, pues con esto añadiremos datos a la base de datos.
And so now we will get a subset. We said we're just going to use 10K, right? And then what we're going to do is iterate through our questions, okay?
Y básicamente buscamos el final del batch, del conjunto de datos este, y creamos una lista de IDs, creamos los metadatos del batch, creamos los vectores utilizando el modelo y juntamos estos datos en lo que serían el vector en sí.
find the end of the batch that
Y aquí
we're looking at,
añadimos a la base de
generate
datos.
IDs for each vector. Each vector inside of Pinecone needs a unique identifier. In this case, we'll just use the index number. We'll store inside the metadata feature of Pinecone the actual text from the question next to the vector embedding, and then use the model that we created above to generate the vector embedding and store it all together. So think of it as a tuple of an ID, a vector embedding, and the metadata that goes with it. And we'll actually zip up that tuple using zip and then upsert it into Pinecone. And so if we run this, you'll see TQDM kick in, and this will upload all of our embeddings into Pinecone. This will take a minute to upload. There's a lot of data here that we're uploading, as well as the model has to run. So there's some encoding for the model that has to happen. There's a round trip that has to happen to Pinecone. So we'll just wait here for a minute for that to happen.
Sí, pues esto tardará.
All right, so that finished.
3
And
minutillos.
let's check to see what we've stored. So there's a function called describe index stats. And we have 10,000 vectors, just as matches what we have here above inside a vector limit. So that worked great. So now we can finally get to the point where we can ask questions. And so I've defined something very small that we'll use here that executes queries for us called run query. And all this does is takes the text version of the question that we want to ask, that's query, builds a vector embedding out of it that we'll need, and then runs the query against Pinecone. So the question has become an embedding. We pass that embedding into Pinecone. We ask for the top K. In this case, we're asking for 10. You can feel free to change that to any number you like. You can get more results back. And then we ask for the metadata, which actually had the question in it, right? It's useless for us to just look at the vector embedding. We actually want to see the text as well. And so that's what's inside of the metadata. And we want to say include values equals false, because what that does is it makes it so that we don't get the embeddings back, because there's nothing to do with them. They're just being used to find similarity. And then what we'll do is iterate through the results and then print them out. Okay, so now let's actually run a query. So which city has the highest population in the world? All right, worked great. So we got back a bunch of similar questions. What is the most beautiful city in the world? Which country has the fastest growing population? All of that is relevant and works great. And we can come up with other sort of silly examples to see that our system works well and it's extensible. How do I make a chocolate cake? It's just sort of a random question I came up with. And then we just call run query again. All right, how do I make a delicious cake? How do you make a 10-inch cake? These are all relevant questions as well. So that's it for this lesson. We built a semantic search system top to bottom using Pinecone. We embedded the titles from the questions from Quora, and we built something that will be extensible and that you can reuse over and over again. In the next lesson, we will build a RAG system, or retrieval augmented generation, using Pinecone and OpenAI.
Vale, pues nada, esto no ha terminado, bueno, quedan 20 segundillos y la idea es que esto, pues almacenaremos todos estos vectores de todas las preguntas del dataset este, y pues después ejecutaremos la query, estas dos queries de aquí, que preguntan qué ciudad tiene la población más grande del mundo, y aquí vemos los datos del índice. Tiene 384 dimensiones, hay 10.000 vectores, y aquí ejecutamos esta query y obtenemos preguntas similares. Aquí, como vemos, cuál es la ciudad más sola en el mundo, con más de 1 millón de habitantes por metro. Y esta es en principio la más similar, y la última es qué país tiene las chicas más atractivas, y nada, pues esta es más parecida a la población. Y aquí, cómo se hace un pastel de chocolate, es cómo se hace, cómo se pone en el horno en 10 minutos. Sí, pues básicamente aquí pues encuentra el vector más similar. Nada, vamos a la siguiente lección.
In this lesson, you will build a RAG system, or Retrieval Augmented Generation System, using Pinecone. You will work with a sample dataset of Wikipedia articles and build vector embeddings out of the articles. Then you will look at what search results look like by doing a simple document retrieval from Pinecone. Then, while working with OpenAI, you will build a nicely summarized article out of these results. All right, let's dive into the code. Now we're going to build a classic Retrieval Augmented Generation, or RAG, system using Pinecone with OpenAI. And it's going to look something like this. So we have our happy-faced user that we had in previous lessons here on the left. And what he's going to do is ask a question against a data set that we will have prepared and stored in Pinecone. And in this case, we'll ask what was the Berlin Wall. And similar to other lessons, we got back long responses or documents from Pinecone. But it'd be really nice if we could take some of those long responses and get a summarized version of them. And what we'll do...
Pues nada, ejecutamos aquí el código, ejecutamos los imports requeridos, obtenemos la API key, generamos el índice, aquí nada, aquí cogemos el dataset.
Do is show how to build and do a little bit of prompt engineering out of the responses from Pinecone, send those back into the prompt of OpenAI, and get back a beautifully written response from OpenAI. And this is really just RAG in a nutshell. And I definitely encourage you to try different versions of doing prompt engineering. Ours is just a...
Pues en principio lo que vamos a hacer, vamos a enviarle una pregunta a la base de datos. El vector va a encontrar la respuesta más similar y después con esta respuesta se la enviaremos a la API de OpenAI y tendremos distintas respuestas.
A fairly simple example to show you what it might look like. So let's get started. So what we're going to do is first clear out warnings. So you've seen this previously before, where we import warnings and filter out the warnings. And this is just to keep things clean for us. So then we're going to pull in the packages that we rely on. And again, we have our deep learning AI utils package that manages keys from OpenAI and Pinecone for us. And then we're going to set up Pinecone similar to how we have before. So we're going to get the API key as so. Okay, now that we have our Pinecone API key, we are going to, as usual, connect to Pinecone. So first connect to Pinecone, then get the index name using our utils package, and then delete our index if it already exists, and then create the index, and then finally get a pointer to the index that we just created. Let's look at our index name, just for fun. All right, something long and unintelligible, but that's okay. It works great nonetheless. So now we're going to download our data, and we've prepared that ahead of time so that you don't have to watch us download data, sort of like a cooking show in that sense. So it's just wget -q for quiet.
Y aquí, bueno, el vídeo sigue.
And the output file will be called lesson2wiki.csv.zip, and it's a file sitting on Drop. So once we of the article, so we'll iterate through the data frame. We'll use QDM again to get a progress.
Nada, vamos a iterar sobre estos datos. Generaremos aquí. Bueno, cogeremos una parte de los datos.
Bar, okay. And then we will get the metadata from it. Because that's a string, we're going to use literal eval from the AST package to get a dictionary back. Okay. And then we're going to append it to what we just created. And this is how you create a vector embedding in Pinecone. Is this long dictionary of values that I cut and paste here because it's so long, but I'll explain it to you. So what we have here is really a tuple again. You have an ID that's a unique identifier for the embedding. You have the values, which is really the vector embedding itself. And then you have
Aquí,
metadata. And we just took the metadata that we had from the line above, and this is the article
añadiremos nuestra
information.
clave
Now what we're going to do
del
is
ChatGPT.
upload that data into Pinecone. So what we want to do is do it in batches. So
No sé
if
si
the
esto va a
length of that
generar.
prepared array is greater than 200,
Pues sí, parece que esto genera una clave de OpenAI de ChatGPT. Sí.
we're going to do it in batches of 200. Then we're going to insert it into Pinecone. Okay. And then once it's inserted, we're going to clear that out so that we can do it all over again. So again, a Pinecone embedding is really three things. There's the ID, that's unique identifier for it. There's the values, that's the
Aquí lo que hemos hecho es tenemos la query, generamos aquí el vector de esa query. Aquí buscamos la query que hemos creado en la base de datos y aquí pues tenemos el texto de respuesta, que es todo esto. This was selected. Sí, parece texto basado en Berlín, básicamente.
the vector embedding, and then there's metadata that goes with the vector embedding. In this case, it's the article metadata. Okay. And now what we're going to do is upload data in batches of 200 vectors at a time into Pinecone. So we'll check to see if we've stored 200 elements into this prepped array, and if so, then we upsert this package that we created. That for me, but I'd love to hear from all of you out there taking the lesson what. And wall. Okay, and then we will build an image to 5 or 10 or whatever you want to look at. In this case, I only want to see 3 for demo purposes. And then we want the article data itself, and we're going to extract out from the matches object the text inside the metadata. So that's what use it for our homework assignment or helper function that we just asked for. Okay, we'll run this all over again. We just did this, but that's okay. It's fast. We're going to run the query.
Pues aquí tenemos la query. Escribo un artículo titulado que es el muro de Berlín. Y aquí pues con esta query tenemos el vector. Con este vector lo buscamos en la base de datos de Pinecone. Tenemos las respuestas. Aquí pues tenemos una lista de las respuestas del contexto. Y aquí le diremos al ChatGPT que nos responda a las siguientes preguntas.
And now we're actually going to build our prompt. And this is going to be prompt start is going to our end. And our end is basically the question, right? That we answer the question based on the context below. We have context, which is the results we got back from Pinecone.
Y este es el artículo. Responde la pregunta basada en el contexto, en el siguiente contexto. Texto. Contexto. Vale. Mira, aquí empieza el artículo. Espera. A ver. Start question. A ver, vamos a una búsqueda rápida para ver dónde está la pregunta. Sí, aquí tendremos la respuesta.
And then we have the end, which is question colon.
Pues este es el artículo el artículo con el contexto que hemos sacado de la base de datos. Bueno, no está mal. Aquí no está mal. Parece que Top K3. Esto seguramente... Esto seguramente nos dará las los tres vectores que se acercan más a este vector que hemos enviado aquí, que es el muro de Berlín, básicamente. Y nada, pues...
Now, what's the question we're asking? In this case, it's what's the Berlin Wall, and then we're asking it for an answer, and that will be stored in the tuple named prompt.
Pues nada,
And let's take a look at what we have.
básicamente esta lección es esto. Vamos al siguiente capítulo, que parece ser un sistema de recomendaciones.
In this lesson, you will build upon what you have learned in previous lessons. You will work with a sample dataset of news articles and build vector embeddings out of the article titles. You will then build a recommender system that will search across all article titles and retrieve the titles that are most relevant. You will then build upon that even further by building a recommender system based on the article content rather than the topic. All right, let's go. So we're going to build a simple recommender system, and it's going to look like this. And we're going to do it in two parts. First, we're going to take a series of news articles and build vector embeddings out of them and put them into Pinecone. And then we'll ask it about Obama, a very simple query. And we'll get back some results, 3 different articles. And this will be a title-based search. In other words, we're going to look for Obama in the title of the article. Then we're going to check to see if we can do it slightly differently. And so what we'll do is we'll take the data that we uploaded in the Pinecone, we'll query Obama, but this time we'll do it against the article content itself rather than the title. So let's get started. So what we'll do, we'll take the...
O sea, en esta lección lo que vamos a hacer básicamente es, con los artículos que tenemos, generaremos unos vectores que guardaremos en la base de datos de Pinecore, y a la base de datos le haremos una búsqueda que será Obama, y con esto pues tendremos una lista de artículos. Y con estos artículos generaremos artículos de noticias y los guardaremos en la base de datos.
The data that we uploaded in the Pinecone, we'll query Obama, but this time we'll do it against the article content itself rather than the title. So let's get started. So what we'll do, we'll start off by cutting off the warnings as we have in other lessons.
Aquí pues básicamente ejecutaremos los imports. Cogeremos la clave de Pinecore y de ChatGPT, y aquí pues obtendremos el dataset. Aquí vemos que el dataset pues tiene las siguientes columnas. Aquí también pues básicamente fecha, año, mes, día, autor, título y artículo. Y aquí con el link, la sección y la publicación.
And then importing the Pinecone and OpenAI API keys. And so we'll just look at the header. CSV called all later on, and we'll prepare our utils package. Okay.
Pues aquí ejecutaremos y tendremos el cliente de ChatGPT, aquí las utilidades que nos proporcionan, aquí crearemos un índice en la base de datos, y aquí instanciaremos la base de datos. Aquí, en caso de que el índice exista, lo eliminaremos, y aquí pues aquí crearemos el índice, y aquí pues le pondremos
and then get our index name from the utils package. Okay. And then get a pointer to our Pinecone object. And then this is boilerplate at this point, so we'll just copy and paste this in. But again, we check to see if the index name already exists. If it does, we delete it. and then we create it because we just deleted it. And then finally,
aquí crearemos los vectores de dataset que tenemos, y aquí cogeremos una pequeña parte del dataset que estamos utilizando. Básicamente aquí lo partiremos en trozos, cogeremos los títulos, de los títulos los convertiremos en vectores, y aquí tendremos los datos preparados.
we'll get a pointer to our pinecone index. And then run that. You saw this function in an earlier lesson, but we have something called get embeddings, and this is just a wrapper function for OpenAI to return embeddings from a list of text. In this case, that text array is called articles, and so we'll declare that. It's called get embeddings. And then what we're going to do is prepare and insert the data. So we'll iterate through the data frame, we'll read it number of rows at a time, build an embedding out of it, and then upload it into Pinecone. So this is a lot of code. It's about, say, 12 to 15 lines of code. So I'll copy and paste it in, but walk you through it. So we're going to read the CSV file called all the news-3. This is the one that we've been working with earlier, but we're going to read it chunk size, rows at a time, to make it manageable. Okay, and just make the.
Parece que esto tardará un poquillo, unos 2 minutillos.
It's a little bit easier to read by putting that there, and we're going to read at most 20,000 rows. Okay, then what we're going to do is iterate through the chunks one at a time, and remember, chunk size is 400. So what we're going to do is get the titles out of that data frame chunk, right? A chunk is just a subset of the larger data frame. Okay, and then we're going to get the embeddings for all of the titles that was declared here, and then prepare a pinecone embedding, or an array of embeddings as we have before. And this is just, simple Python syntax, right? For I in range through the number of titles, create an embedding for each one of them, right? Then we're going to increment chunk num, because that's what helps us get a unique identifier for the embedding. And then we're going to upload it 300 at a time. So if we.
Y pues básicamente aquí lo que está haciendo es lo siguiente. Una vez tenemos la parte, una lista más pequeña de toda la lista que hemos tenido de la base de datos, pues la iremos subiendo al índice en trocitos de 200, básicamente.
We get to 300 or exceed 300 number of vector embeddings inside the prepped array, then we're just going to upsert it into Pinecone and then delete or clear out that prepped list, and then update the progress bar for TQDM, which we've declared up here. So let's go ahead and run that. This is going to take around 3 minutes on our machine, as you can see here, but we'll speed this up in post for you so that you don't have to sit here for 3 minutes and watch it. Okay, so that has completed. We upserted 20,000 vector embeddings in the Pinecone, and now we will look at what we uploaded. So let's say index dot.
Pues esto es un curso de. Mira, a ver si te paso el link. Mira. Es este curso. Digamos que aquí están los cursos. Y pues son gratuitos, y guardas aquí en la. Digamos que en el curso pues te explica cómo construir aplicaciones con bases de datos de vectores, y pues esos vectores al final es texto que lo convierten a vectores, y con esos vectores en la base de datos pues tú buscas texto, básicamente. Y pues aquí en el curso pues te enseña búsquedas semánticas con el texto, aplicaciones para generar texto parecido, sistemas de recomendaciones. Y nada, a ver qué nos enseña el curso este. Esta parte de código ya la hemos ejecutado. aquí vemos que la lista está, los vectores que tenemos aquí en el índice pues tienen dimensión de 1536 dimensiones. Hay 10.000 vectores aquí y con esto pues obtendremos las recomendaciones. Con esto, con el índice, le pasaremos el índice de la base de datos, lo que queremos buscar y obtendremos los 10 resultados. Y a ver, por ejemplo, aquí le estamos pidiendo que nos dé recomendaciones con este índice que es nuestra base de datos de Obama. Y a ver qué nos da.
Describe.
Pues mira, aquí con lo que tenía en la base de datos, nos dice Barack Obama, just stepped off of the sidelines para defender el Obamacare. Bueno, vamos, que nos devuelve artículos parecidos al texto de Obama, básicamente. Y seguimos.
Index stats. And yes, we had 20,000. So that's perfect. So let's declare our function again that gets embeddings from OpenAI. We've seen that function before. And let's actually get some recommendations. So I will go ahead and paste in this helper function that we've created here called get recommendations. And what it does is takes a pointer to Pinecone, what you want to search for, the number of elements that you want to return inside of top K. In this case, we'll default to 10. Gets an embedding out of the search term that was passed in from that helper function declared above, executes and returns the results from a Pinecone query. And what we'll do here is look for data about Obama. Okay, so we declared that function. And so let's say recommendation equals get recommendations are Pinecone index and something about Obama. And for each result in the recommendations, which is returned inside of the matches element, we'll say print the score, which is the similarity score coming back from.
Final, este número de aquí es lo parecido que es este texto a la búsqueda que hemos hecho, que es Obama en este caso.
From Pinecone, and the metadata that we stored inside of Pinecone next to that embedding. Okay. All right, so we got back a bunch of information based on the titles of the articles about Obama. Obama's been a much more effective communicator than he gives himself credit for. That is delete our index first. So you saw this piece of code, you're familiar with it at this point, right?
Vale, pues aquí volvemos a crear otro índice. En caso de que el índice exista, lo eliminamos. Creamos el índice. Y con esto creamos aquí el vector parece.
If the index is there, we're going to delete it, otherwise create it. Nothing different there. And so what we're going to do is somewhat involved, and I'm going to walk you through it. So let's first declare a function called embed that takes an array of embeddings, a title, an array that's going to store results into, and then a counter called embed number. And I'll walk you through how this works in just a moment. But before I do that, let me paste in the code that actually uses it. So what we're going to do here, I'll jump down here to the bottom. We're going to iterate through all of the articles list from our data frame that's declared here. Then we'll grab an article and we'll grab the title that goes with the article. If the article is not none or null, what we're going to do is use the recursive character text splitter from LangChain. And we're going to use that to effectively chunk up the article of interest into 400 characters at a time. And an overlap of 20. And then what we're going to do is call this embed function that we declared up here. So let's store that. Okay.
A ver, pues básicamente con estos datos que son los vectores, cogeremos los datos de los vectores y los añadiremos a esta lista de prepet. Y los iremos subiendo al índice por bloques de 100 y nos devolverá el número de vectores, básicamente. Aquí pues partiremos el texto en este caso con este objeto recursive character text splitted, que le diremos que queremos partir el texto en 400 caracteres y que se coja un overlap entre un texto y el otro de 20 caracteres, parece ser. Y pues aquí leerá este SV y obtendremos la lista de artículos y de títulos.
So as we split it up into smaller chunks, we're going to get the embeddings for each one of those chunks by calling get embeddings, which is declared above, and then we're going to call embed. Okay, and so what embed does is it walks through this array and stores the vector embedding for each one of the chunks into the prepped element. And if it hits, and you're used to this pattern at this point, if it hits 300 or more elements inside of the prepped array, then we're going to go ahead and upsert that data into Pinecone and then clear it out so we can do it all over again. Okay, so we ran this, I believe, and let's go ahead and run this code. So this is going to run and take quite a bit of time. It's going to take around 5 minutes or so, and we will fast forward that for you so you don't have to watch it upload, and we'll be back in just a moment. All right, so that finished uploading, and now we're going to make sure that after we previously cleared out the index that our upload worked. So, all right, 10,500 vectors were uploaded. That's great. So what we'll do is run the same exact code almost that we already ran, except the main difference is that we're going to keep this small dictionary called scene. And the reason that we're going to do that is because if you recall, we actually split up the article into chunks using LangChain. And what we want to do here is keep track of what we've already seen so that we don't get the same article being returned twice. So we're going to say if title.
Bueno, básicamente las recomendaciones que obtenemos es si le pasamos Obama.
Not in scene, then we will actually print out the score of the.
Si le pasamos Obama, pues nos devolverá las recomendaciones. Después aquí iteraremos las recomendaciones y si el título no está dentro de estos vistos, lo imprimiremos por pantalla.
Search as well as what we got back from our search. And then we'll say like, hey, we've already seen this article. Okay, it's very simple. Just put a dot in there to keep track.
Bueno, pues básicamente
lesson we're going to build out.
Hace eso. Devolver la similitud entre vectores. A ver, búsqueda híbrida. A ver qué aprendemos aquí.
This lesson is all about hybrid search. You will leverage a feature in Pinecone that allows indexed entries to have both dense and sparse embeddings at the same time. Of course, this means we can also search across sparse and dense at the same time as well. To do this, we will leverage BM25 and Clip to generate embeddings from fashion products to search across both text and image product descriptions at the same time. Let's get coding. We're going to build a hybrid search system using Pinecone. So Pinecone supports vectors with sparse and dense values, which allows you to perform hybrid search. In this lesson, we're going to teach you how to use hybrid search, which is the ability to combine vector and semantic search with traditional keyword text search against different modes.
Pues aquí básicamente podremos hacer una búsqueda de texto y pequeñas imágenes a la
Modalities for the
vez.
same entity. And this example will show you exactly what that means. So we have our user here on the left-hand side, and we're going to take data from a fashion product database. And we're going to encode it into two different types of vectors. The vectors that we've been using previously are what's called dense vectors. And to do that, we'll use something called clip, and we'll get into what that is later on. But this time we're going to generate what's called sparse vectors. And to create that, we'll use BM25, which is a common encoding technique in information retrieval, but we'll talk about what that is later.
Pues aquí, como vemos, este dataset tiene pequeñas imágenes y aquí pues cogemos las imágenes y mostramos por pantalla la imagen 900 y pues esta es la imagen y estos son los datos que tenemos aquí. Parece que aquí pues describe que la imagen es de un hombre que lleva accesorios o lo que sea, su categoría lleva relojes, el color, la estación y el año, el estilo y el producto.
The key point here is that for any given row in the index of Pinecone, you can store dense and sparse vectors at the same time with the metadata that goes with it into one row. Then what we're going to do is query for dark blue French connection genes, and we'll get back a data set from Pinecone, which will have some genes, obviously. And then we'll tune what's called the alpha parameter inside of that query to change whether we weigh the results from the BM25 encoding or the clip encoding more or less, and we'll see how the results change. So let's get started. To get going, we will go ahead and import in our warnings cutoff mechanism here. So import warnings and filter warnings. And then this time, there's our data. And that to text, it uses term frequency. We're going to get back a caption. So let's get started. Turn the best caption 25 with Pinecone.
Básicamente, el BM25 es un codificador de imagen, parece ser. El display name, aquí obtenemos el índices, valores. A ver.
Cone sparse dense vector.
No, el BM25 es una función para rankear que se usa para devolver texto estimando la importancia en términos de texto con la búsqueda que hacemos. Está calculada, y aquí según nos dicen está calculada con el número de documentos que hay en los datos y la frecuencia de palabras entre diferentes documentos.
For use in hybrid search. Clip, on the other hand, is a neural network devised and created by OpenAI, built on millions of images and respective descriptions that can return the best caption for an image, right? So given an image, we're going to get back a caption. So let's get.
Y en este caso, aquí creamos el vector y aquí pues hacemos la búsqueda de este texto y nos devuelven qué índices es más parecido. Y aquí en Code Documents, ¿esto qué es? A ver. Vale. Pues aquí. A ver.
millions of images and respective descriptions that can return the best caption for an image, right? So given an image, we're going to get back a caption. So let's get started with that. So we're going to create frequencies to determine fascinating millions of images. So let's get started with that. So we're going to create a BM25 encoder, and we're going to fit our data to the metadata that we just looked at above. Okay. And then we'll look at the product display name. Turtle, check, min, navy, blue shirt. All right. That's a product display name. Makes sense. And now what we're going to do is do two different things. First, encode queries of a product display name and look at what we get back. All right, so we've encoded queries, we've encoded documents, and now we're ready to get going because we've completed our work with BM25.
Pues sí, hemos codificado los documentos. Y aquí pues crearemos un vector utilizando clip, que como ha dicho es un modelo creado por OpenAI, entrenado con imágenes, con pares de imágenes de texto y, bueno, texto e imagen.
Descriptions that can return the best caption for an image, right? So given an image, we're going to get back a caption. So let's get started with that. So we're going to create a BM25 encoder, and we're going to fit our data to the metadata that we just looked at above. Okay. Do two different. So with the model.
Vale, pues aquí.
All right. So
obtenemos el modelo. Con este modelo codificamos este dato. Aquí tenemos las dimensiones del vector y la longitud de fashion, que es pues será el dataset. Sí, el dataset. Y aquí crearemos vectores utilizando tanto los vectores sparse, bueno, BM25 y los vectores del modelo de OpenAI. Esto parece que tardará un ratillo.
512 dimensions in that dense vector, which is exactly what we wanted to see. So now let's go back to our fashion data set. Okay, we're going to see how many elements that we have. We have 44,072. And so this is going to be the first time inside Pinecone that you see us uploading sparse and dense vectors at the same time. The way that you do that's actually not too different from how you upload normal vectors. It's just that you're going to add sparse and dense at the same time, as you can imagine. So a bit of code to do that. I'll walk you through it, but I'm going to go ahead and paste that in for you so you can see it. So we're going to do it in batches of 200 like we have before. For each one of the elements in the batch, in the fashion data set in batches of 200, we're going to get pointers to the beginning and end of the batch that we're going to use, extract the metadata, convert the metadata, and then build metadata fields that are ready for upload. We're going to take the batches of the images. We're going to encode our sparse vectors using the encode documents function. We're going to get our dense vectors using the model encode function, convert that back into a list, and then get our unique identifiers for each one of the vectors, right? So if you remember, each Pinecone vector embedding is a combination of an ID, the vectors that it represents, and the metadata that goes with it. So this is the metadata up here. This is the
Pues básicamente tenemos los metadatos, concatenamos todos los datos aquí. Acá tenemos todos los datos aquí en el metabatch. Extraemos la sublista de imágenes, y creamos vectores de las imágenes. Aquí pues utilizando el BM25 y aquí con el modelo. Y con esto tenemos los identificadores. Y aquí pues crearemos los datos y crearemos el diccionario para subir los documentos a la base de datos.
Vector embeddings here, and this is the unique identifiers for the embeddings. The only difference here is that we have dense and sparse at the same time, and you're going to see that we can upload them down here in the append function below. So what we're going to do is zip up all of that data that we just created above, right? And then we're going to append it inside of a dictionary object here in upserts.append. Okay, we're going to keep on adding these through as we iterate through the for loop and then do an upsert into Pinecone. And then we'll see what we got back after uploading all.
Pues nada, básicamente hemos subido todos estos documentos, todo este diccionario de estos datos a la base de datos. Y aquí pues tenemos que estos datos tienen dimensión de 512 y tendremos 900 datos. Y ahora pues ejecutamos esta query. Dark Blue French Connection Jeans for Men. Y aquí pues nos devuelven imágenes. Parece que con este texto tendremos que obtener imágenes de pantalones negro oscuro. A ver. Pues sí,
All that data.
esa es la idea.
So let's go ahead and run that and look at it. And the result of that query is going to be the images. So let's go ahead and put in this as we had hoped. Okay, but now let's balance the search a bit, right? We talked about this alpha parameter before. What you want to do is know that controlling alpha relies on sparse or dense more. Let's go ahead and run that to 1 and changing it. It's, you could change it from 0.2, you can make it 0.5. It's really up to you. But for illustrative purposes, we're going to make it 0 and 1 just to make the example fairly obvious. So let's go ahead and run this and make it more sparse this time. So we'll run that. You'll see in our results, we got back women's jeans, which is perhaps not exactly what we wanted.
Podemos hacer la prueba. Dark Blue French Connection Jeans for Men. Pues vamos a buscar pantalones rosas. French Connection Jeans for Women. Vale. A ver qué tenemos aquí. Bueno, seguramente no tenemos muchos datos de pantalones rosas, así que nos saca esta tira que es rosa, pero aparte de eso, otra cosa más.
We're looking for men's jeans up here, and let's confirm that by looking at the titles and execute that query. And yep, we got exactly back what we had hoped. Okay, so whether we rely on sparse or dense more. I encourage you.
A ver, aquí es una búsqueda híbrida. Y dense es un array representando los vectores, seguramente. Diccionario de los índices y valores y alfa. Vale. Aquí en principio pues parece que pues haremos la búsqueda tanto por por el BM25 o el modelo de OpenAI, Flip.
To look at this code when you're offline at home and look at it. What you want to do is know that controlling alpha relies on sparse or dense more. Let's go ahead and run.
Bueno, parece que esta búsqueda es mejor. A ver si le ponemos inference next engines for woman. Sí. Sí, esto es la descripción de estos pantalones, básicamente. Así que bueno, pues podemos hacer una búsqueda por imágenes con el texto. More sparse. A ver.
Run that. Okay. And run the query one more time, but with.
Pues nada, aquí ya se va los datos y vemos que aquí el resultado pues no se parece en nada.
Different amount of alpha. So what we'll say is, that's the question. We're going to put in dense and sparse, and then we'll run our query one more time. And then view the images. Before running the code, we're going to set alpha to 1, and we're going to run that code, and we get back our images. It's perfect. And what we're going to do now is check to see whether we got back more men's jeans. And so what we'll do is go ahead and copy and paste this in and execute that query. And yep, we got exactly back what we had hoped. Okay, so let's actually execute the hybrid scale function here and look at the results that we got. Now, remember our alpha parameter, it's actually a continuous variable on the range of 0 to 1. And I challenge you or encourage you actually to play with what different results you get from changing it. It's, you know, you could change it from 0.2,
sí,
you can make it 0.
Cuando alfa es 0, el resultado pues básicamente no es muy bueno. Y con 1 parece que obtenemos mejor resultado. A ver si hacemos 0.5. Pues sí, pero justamente el pantalón que se parecía más, pues no lo tenemos. Y nada, vamos a la siguiente lección.
In this lesson, you will have fun with the age-old question of, to which parent the child looks the most similar?
Y aquí pues lo que vamos a hacer es a ver a qué padre se parece, aquí veremos a qué padre se parece más el hijo.
To do this, you'll answer the question by using vector embeddings. You'll use a freely available image dataset, in particular one of the British royal family, and use science to determine if Prince William looks more like King Charles or Princess Diana. It's simple and extensible enough for you to try on your own family pictures. Let's have some fun. We're going to build a facial similarity search system to compute which parent looks most like their child. So we'll take a father.
Sí, pues aquí tendremos el príncipe Carlos, la Diana y el príncipe, bueno, sí, príncipe Carlos, básicamente. Utilizaremos el modelo FaceNet.
We'll take a mother and we'll take one child and see whether the child looks more like their father.
Y aquí pues generaremos vectores. Hay este archivo de vectores. Y lo abriremos. Y seleccionaremos persona. La persona. Esperaremos. Y obtendremos el vector face. Este face que es. Vale. es lo que nos dará el vector. Básicamente este objeto nos dará el vector de la imagen de la persona, seguramente.
Now I've prepared a data set for you ahead of time. And as usual, I will not make you sit there and watch me download the data, but similar parameters to wget, make it quiet, show the progress. I'll put the file name as family_photos.zip and pull it off of the location that I've specified here. And you run that, and then we will unzip the photos as well. Okay, perfect. Make sure that you run the query like this. It'd be uncommented, right? But for this lesson, we'll keep it commented out so that I don't accidentally run that for you. The data has been already downloaded for you in your notebook. This is how I ran it when I was at home before we prepared it, but you already have it local on your disk. And the family photos zip file has a structure of family as a top level directory with subdirectories of dad, mom, and child each. So let's actually look at some of the pictures. I've created a small help.
Vale, pues sí. Con esto estamos escribiendo las imágenes de la persona. Y ahora pues veremos estas imágenes con el vector de la imagen, básicamente.
Helper function to help you see the photos called show_image.
A ver, esta función es para mostrar la imagen, básicamente, y esta de aquí parece que te devuelve la diferencia entre personas.
JPEG.
A ver, vamos a ver qué nos dice de
And
esta
see what we
parte
get.
del código.
So that's a image of King Charles. And now we're ready to calculate some scores and upload data into Pinecone. Before we upload the data into Pinecone, we're going to produce a t-SNE scatter plot based on PCA reduction that's going to give us a really pretty scatter plot of the data so we can visualize it.
Vale. El t-SNE nos mostrará los datos en cómo están organizados de manera de la distancia que hay entre ellos, por decirlo de alguna manera. Básicamente aquí vemos que los padres se parecen mucho, los hijos están aquí y aquí están las madres. Parece que se parecen más a las madres los hijos. Claro. En este caso porque son jóvenes, diría yo.
Principal component analysis, or PCA, reduces.
Aquí pues guardaremos los vectores en la base de datos, crearemos el índice. No, crearemos el índice inicialmente. Y aquí guardaremos los vectores.
Is the dimensionality. Lower dimensional space first, you get a significant speed up in the t-SNE process. For the t-SNE algorithm, perplexity is a very important hyperparameter that controls the number of neighbors that each point considers during dimensionality reduction.
Vale, pues en este caso el perplexity controla el número de vecinos que tiene en cuenta para guardar estos datos, este vector.
And you'll see I actually made it pluggable in the code below. So let's go ahead and do that. So I've created one helper function called gen t-SNE data frame or generate t-SNE data frame. And what that does is it iterates through the vectors.vec file looking for a specific person and appending that to the vectors list. And then what we do is actually do a PCA reduction against a specific person, right? So what we're doing here is a PCA reduction for a specific person who's passed into the function. Then we do a t-SNE reduction as well against that and return that as a data frame to the next function, which we're going to call here called plot tsni. And I'm going to go ahead and plug that in. So plot tsni actually calls generate tsni data frame. And you can see it down here below. And most of this code is just setting up matplotlib. And what we're going to do here, and this is the meat of it, is for each person, right, that we've defined here in this dictionary.
Pues ya hemos guardado los vectores de las personas. Básicamente estos vectores tienen 128 dimensiones y hay 238 vectores. Y aquí pues vamos a calcular la similitud entre vectores, en este caso entre padres, madres e hijos. A ver. Vale, pues vemos que de media el padre se parece 0,41 y la madre 0,34. Y aquí pues podemos ver, vamos a ver el príncipe Carlos, a que se find the closest given, we know that is most similar. Pues vamos a ver el padre se parece más al hijo en este caso. Sí, en este caso sí. En este caso pues es la foto más similar de
Dictionary, dad, child, and mom. And these are just the colors to see how it changes the child. So from the dad. And Princess Diana to their offspring, Prince William, to figure out which of those two looks most like Prince William. The data showed that's actually King Charles that looks the most like Prince William. And at the end, we figured out which image in particular looks most like Prince William. And we saw that this image here at the end looks most like Prince William, which I would agree. Like they very much look similar. I encourage you to play with this code with your own family members and see what results you get as well. In the next lesson, we're going to
Nada, básicamente pues podemos jugar con esto para con diferentes fotos ver qué similitud hay entre miembros de una familia. A ver.
In this lesson, you will build another fun system. This time, you will build a small machine learning model to detect anomalous log entries in Cisco ASA log files. You will train the model using supervised learning against a small dataset we prepared in order to make the lesson more accessible and keep training time.
Pues parece que aquí vamos a entrenar un modelo. La verdad creo que esto podría tardar un poquillo. Así que nada, vamos a ver. Vamos a intentar ejecutarlo primero. Inicialmente importamos todo lo necesario. Aquí obtenemos las APIs. Creamos el índice. En este caso. Aquí. Pues imprimiremos parte del dataset. Vamos a ver qué nos explican.
You will then use the model and feed it a sample input data set to find anomalous log entries. Let's code and innovate. So we're going to build an anomaly detection system using Cisco ASA log.
Vale, aquí en principio pues tenemos logs de datos de terminal básicamente con la fecha y qué ha sucedido. Así que
files. And the way that's going to work is I've prepared a very small training set called training.txt. That's a label data, so we can do a little bit of supervised learning and create a very small model that can detect anomalies against log files. And then we're going to use a sample data set called sample.log that I've also prepared that has one small anomaly inside of it, and we're going to try to see if we can find the anomaly. We're going to run the sample.log file data through our model and store the embeddings as the output inside of Pinecone and use that to find the anomaly. So let's get started. So we'll start by importing our warnings as we always do. Okay. And then our package dependencies. Okay. And then we're going to get our Pinecone API key using the Deep Learning AI Utils package here. Okay. And then we're going to create our index. So same code as always, we get a pointer to the Pinecone instance, and then we'll delete the index, and then we'll create the index as well, and then get a pointer to it at the end. So that's going to go ahead and run. Now, we've already downloaded the data for you in the lesson, but if you happen to be running this offline, you'll need to run this by uncommenting out this line, this wget line that pulls down this file called training.tar.zip, but we've already done it at -5, so we can see.
A ver, y aquí parece que usaremos el modelo BERT, que convertirá el texto a vectores de 256 dimensiones. A ver si esto no tarda mucho. No, parece que no. Vale, y aquí con estos vectores entrenaremos el modelo. Que no sé yo si tiene... Ah, sí, parece que aquí el archivo este tiene la probabilidad de que sea una anomalía en este caso. Así, pues con esto podremos entrenar el sistema. Vale, y en este caso pues no va a tardar mucho porque ya hay un modelo preentrenado, el cual cargaremos aquí. Y bueno, y en caso de que no esté, que no tengamos este modelo, pues lo entrenaremos de nuevo. Como esto puede tardar mucho, pues sí, usaremos el modelo que nos dan ellos. Y aquí pues se abre este archivo, se lee las líneas, para cada línea se parte la línea y si hay línea pues se añade a esta lista de samples de líneas. Y aquí pues creamos vectores y los añadimos a la base de datos Pinecone.
See the first 5 lines, the 2 at the end, also delimited by caret. Log sort of identifier, and then the actual log message, right? Now, what I've done is gone ahead and prepared a data set that has been labeled for you based on that log file above. And there's a slight difference. The format of this file is essentially a sample log file and then hat or caret, another log file, and then the label similarity between the two at the end, also delimited by caret. Okay, we are going to only look at the top 5 here. There's some that are labeled differently at the very bottom of the file, and I encourage you to look at the bottom of the file. What this is going to say is that log part here, highlighted here by my mouse, is similar by a score of 1, and so on and so forth. This is similar by a score of 0.9 on a continuous variable range of 0 to 1. Okay. Now we're going to create our very, very small model based on sentence transformers. So inside of our hat.
Vale, y aquí pues en principio put logline. En principio esta línea pues no es una anomalía. Y sleep index query matches. Y aquí pues en principio encontrará la anomalía según entiendo. Bueno, aquí la guardarán resultados y aquí pues imprimirá los resultados. Bueno, aquí imprimirá si es similar o no.
And then we're going to append these samples, right? We called it A and B, right? We had log 1, we had log 2, and then the similarity score, which I'm calling here label. And we're going to store that inside of the input example object. And we're going to pass it the label because this is supervised learning again. We'll do 100 warm-up steps. We'll prepare our data loader, and then we'll set up our loss function. Okay, so let's go ahead and run that. And now we're going to actually train the model. So we're going to call model.fit. That's going to do the actual training. And then we're going to prepare our sample data at the same time. So it's really two parts, but I've clustered it into one cell. So there's the model training here, model.fit. And then there's preparing the sample data that we're going to use to pass through the model later. So this is going to train, and this will run for a little bit.
Y aquí results. Results score. Aquí nos muestra los resultados. Aquí redondeamos la similitud. Vale, básicamente line log. Tenemos los resultados aquí. Sí, básicamente pues tenemos la que menos se parece. En este caso imprimimos el último elemento de los resultados, lo que podría ser una anomalía en este caso. Vamos a ver si estamos en lo cierto.
In Pinecone, a known good log line. So we're going to say good log. Okay. So now let's take that good log line and query it inside of Pinecone, and we're going to get the top 100. Okay. And that's going to come back and be stored and queried. And we're going to get a pointer to the matched values inside of Pinecone and store that in results. Now what we're going to do is look at the results, and we're just going to have a small routine here to print that out. Okay, so iterate through, look at the top 10, and these are the top 10 matches for this line here. Of course, this one matches and has a score of 1 because it's the same line, and these ones look very similar as you can see. Okay, so that's the top 10. Now what we're going to do is take the last element in there. Okay, seg fault detected in like a Cisco ASA log file, except for this message that says seg fault detected in the matrix. And so this is our anomaly, right? The worst performing score that came back.
Y en este caso, bueno, es el último resultado y se entiende que es una anomalía, pero vamos, si todo fuesen resultados iguales, pues seguramente no podríamos definir si esto es una anomalía o no. Bueno, en este caso el dataset está preparado. Y nada, básicamente es eso.
Using Pinecone with Cisco ASA log file data. I encourage you to try it with other types of data using sentence transformers as well and see if you can find anomalies in data. In this course, you learned about the essentials of building applications using vector databases. You built simple search and recommendation systems, retrieval augmented generation, or RAG, explored hybrid search, looked for facial similarities in the royal family, and finally found anomalous log entries in Cisco ASA log files. We only scratched the surface of what's possible with vector databases, and I encourage you to explore far beyond the material we covered today. I'm looking forward to seeing what you've built on your own.
Bueno, un mensaje un poco motivacional, pero bueno, ha sido entretenido ver este sistema de Pinecore, base de datos de vectores. Y nada, pues es una herramienta nueva que descubrir y ha sido un placer. Ahora por eso tarde aquí y ya está entrando el sueño. Así que nada, buenas noches y a disfrutar el fin de semana.